Right, so first of all, this is a work in progress. Thanks. Another thing I should mention, this is work done by two master students working with me. They're both looking for PhD positions. Hope that after seeing the talk, you may consider hiring them if you're looking for PhD students. So Jeremy started with a quote. I'd like to start with a quote too. This ancient Greeks, Leucippus, said the word coming to being as follows: many bodies of all sorts and shapes move from the infinite into a great void, come together there and produce a single wheel in which, colliding with one another and evolving in all manners of ways, they begin to separate like to like. I find that quite interesting because if you do these modifications, it kind of makes sense, right? So clairvoyant sometimes they were. Right. So Joanna just showed a much more modern version of this. This was done by Fritjof Brouwer for his PhD thesis, like in 2008. You see, dust coagulates as it reaches this line here, which is a line of maximum drift. You lose then to the stars, about Stokes number equal 1 as a function of radius. And the way out of this, of course, is the streaming instability. The dust drift is unstable. You build up then these overdensities, and then we are very interested in that because these overdensities, as we know, can reach the critical density to form planets. Right? This has been studied mostly in local models so far. So this is one. This is the first model that tried to do that in more than local. I wouldn't consider that a global model. Actually, them themselves call this quasi-global. It's basically patching together many boxes, and it's not full in azimuth, as you can see here. What I find interesting here in this model is that you can see the structure that shows here in azimuth. They're bigger than the scale of local boxes. Local boxes, usually you would see a zonal flow taking over the, the whole azimuthal extent of the box. So the question is, what would change if you go to a global frame? So some things that are missing then that maybe such model could answer is there a radial variation of the clumps, the planetesimals that are built with the streaming instability? What is the dominant azimuthal mode? Also, this model here use fluid, so not particles, and self-gravity was missing also from this calculation. So let's see then. So let's take one step back. I promised 3D global models of streaming instability, but first let's do global models of streaming, right? So you put grains in a model, and you calculate then what the distribution would look in the end. This is comparing then with the analytical solution by Andrew Uding. The radial velocity here, so the dust drifts in. This line here is measuring where the dust front is. So here is the analytical prediction for the radial velocity. This is the density here of the gas and particles, and the azimuthal one. So here you see the front is where it's supposed to be. Good. Now, one thing that already you can see that breaks down is that as the dust drifts inward, the analytical solution would be close to sonic, right here at the inner part. You can already see that as you get to half of the speed of sound, the analytical prediction breaks down. Right. And so let's see then what happens as you include also a planet then in this case. So we have here two planetary masses, 10 to the minus 4 and 10 to the minus 3. And here then the dust to gas ratio increases from 10 to the minus 2 to 1. As you see, for dust to gas ratio about 10 to the minus 2, the situation looks exactly what we expected, right, from the models that we usually run without dust. Because here, the dust to gas ratio never really gets too close to 1. But as you go to higher, you see that this the spiral will break up here into something that looks like turbulence. The vortices also, they seem to change, and the structure of the outer gap also looks turbulent in comparison with this one. So the influence on the gap carving, what you're seeing here is the black line. It's behind the other lines, but it's tracing the gap carving for a Jupiter mass planet. And these different lines are lines of different dust to gas ratios. So the blue one is dust gas ratio 10 to the minus 4, red 10 to the minus 3, 10 to the minus 2. As you go here to 10 to the minus 1 and dust to gas ratio 1, you see that the outer edge is changed, right? It will be flattened out. That happens because as dust drifts inward, the gas has to move out, right? So that will change the wall here of the gap. The same thing is happening in the inner one too, but it's more pronounced in the outer. As you see here also, this is the dust to gas ratio. So the dust is drifting in, right? As you go here to 10 to the minus 4, that's here. So dust to gas ratio 10 to the minus 4, it never really gets to influence the gas much, but the higher dust to gas ratios, they are influencing the gas, so they drift slower than in the calculations with less dust. As you see here, these things, the change in the profile of the gap happens when you reach a dust to gas ratio of 10 to the, of 1. So the green and the cyan here, they could change the profile of the gap because they are crossing the line here, dust to gas ratio 1. The other ones, they are not making it there, so they don't change much. The 10 to the minus 2 is barely making it there. As you imagine, as you make this bigger and bigger, there will eventually be a threshold where you can accumulate enough dust here so that you will reach dust to gas ratio 1 for any dust to gas ratio that you start with, have a big enough disk. So the modifications of the gap there, as you see. As I said, yeah, there is a pebble drift that is slowed down or halted in here for this. So what is halting the dust drift? Is this a plot that I, did a quick and dirty plot that I did some time ago, showing what is going on there. So what you have here is the gas density. That's this line here. The dust density is in the dashed line. This is the initial dust density, so 100 times less than the gas. And this yellow dashed line is in the middle of the calculation. As you see, the dust is drifting inwards. And there was a bump here where the dust got trapped, right? And the yellow solid is at the end of the calculation. The dust is drifting inwards and being lost. But this one, at the end of the calculation, is still there. And you see here, you have a little bit of a pressure bump that is trapping it. So that is indeed when the dust to gas ratio reaches about 1, right? So you generate the pressure bump and you can trap it. That's then what is slowing down. Okay. Another thing that we see in these models is Rossby wave instability at the dust front. As the dust is drifting inwards, there is a discontinuity between having dust and not having dust. The back reaction then in this side will be quite strong, and here it will not. So that leads then to a discontinuity in the flow, and as we know, this is very prone to Rossby wave instabilities. As we see here, there is three vortices forming here in this calculation. Convergence is an issue. So this is a plot done by Jeff Fung. And the gap here, you can keep calculating it for a long time. The dust just, the gap just keeps getting deeper and deeper. Convergence for this model, which was alpha 10 to the minus 3, eventually is achieved when you have more than 15,000 orbits. So the lines here for 16,000 orbits is a black, and the purple one, 20,000. So you have to calculate for a long, long time to achieve equilibrium. Another thing I'd like to highlight is one thing you see them, and it was touched upon here in the conference room. As the dust drifts inward, you would expect that the grains would be trapped right in the outer part. As you see, that happens for this case, but not for this. So this dust here could drift past the planet. I found that very strange. Turned out that what is going on is a competition between the drift time. So yeah, the planet here behaves as a dust dam, and this one doesn't. What's going on is a competition between the drift time and the orbital time, right? The dust is drifting inwards, the planet is going around. If the dust drifts so fast that the planet does not have time to go back, the dust will drift past it, right? So you can estimate this, the drift time against over orbital time, and so you can analytically estimate. Q here is the mass ratio, H the aspect ratio of the disk. It's the power law of the pressure gradient and the Stokes number. So these numbers will be about 1. What matters the most is that the aspect ratio, of course, the temperature of the disk and the mass ratio. For this case, this number was above 1. For this was a hot enough disk that theta was less than 1, so then the dust could drift inwards. Of course, we do not expect the disk to be that hot. You would need the temperature here to be quite high, but if you are in the outer disk, the orbital times can be quite large, right? So then in this case, dust then could drift past planets. So this is okay. So we go in the streaming. This video here is very low resolution, as you can see. You forgive the students; they are ESL learning, as we all are. So this is a preliminary model of the streaming instability in 3D. As you can see here, the resolution is low. And to get the wavelength resolved, we had to go to very high aspect ratio of 0.3 here. So that's unrealistic, but that's just a preliminary model. This model had 12 million particles, and we could resolve here the streaming wavelength with 20 grid points. It's good. One thing that we see in this model is that this is a way to get the disk to go denser in time. The reason is because the dust drift is not divergenceless, right? So the inner dust drifts with a lower speed than the outer, so you increase the dust density with time. As time goes in, dust drifts inwards. In the end, then you get the high densities to generate this streaming. So the structure that we get here then in this model, as you can see, it is not an M equal to 0 mode, but the structure, the forms, they are bigger than the usual size of local boxes, right? So one would need to take that into account. We form planetesimals in here. So this model did not have gravity, but the drag force by itself is enough to concentrate the dust and form very massive clumps. So this is a clump which is around here somewhere. As you can see, the resolution is low. All the dust is in one grid cell. This clump there had a mass comparable to Ceres. The mass is not converged yet. It's growing, growing, and growing. But it's already more than the Hush density, which in this model was about 1,000. Another thing that we see is as the dust drifts inwards, we put here an artificial boundary for the dust. Once it crosses this boundary here, it will be gone from the calculation. What we did not expect, or maybe we should have expected, is that again that will lead to a discontinuity in the drag force back reaction, and that also triggers a vortex in the inner disk. So the outer one, one can argue that that's artificial, because there will always be dust out in the outer disk. But the inner one could actually be real because there is something called dust sublimation, right? When the temperature gets very high. So in this side, there is maybe one point where you have dust and another one where you don't, and that could trigger then the Rossby wave instability in the inner disk. So Jake, so then we pass to the other part of the talk. Jake mentioned that also the angular momentum that is seen right in planetism. I mean in Kuiper belt objects, the distribution seems to be 80% prograde and 20% retrograde. This is a plot that is in this article here by Grundy. I call it a protractor plot. What you see here is, so from 0 to 90, the objects are prograde. From 90 to 80, they are retrograde. It seems that there is a transition, actually, as the binaries go to more than 0.05 of the Hill radius. Inside here, you can see the 80-20. Beyond that, it's low number statistics, but it seems that it goes more to 1-to-1, prograde, retrograde. This is the inner ones, so the tight ones and the wide ones beyond that is 0.05, and compare them to a random distribution. So we look at that too. This is data from Chao Chin. See here, so we had the clumps that are formed in the calculation. We try to check if there is a correlation between the angular momentum of the clumps and the vorticity of the gas, which is what is shown here on this plot. Let me put this up. Turned out that if you really want to believe that there is one, you could maybe see it, but I would claim that there is no preference for prograde or retrograde in this case, especially for the high mass ones, which is given here by the size and color of the dots. Anders, he calculated this video here. I think this video is buffering. So let's wait for the video to buffer. I don't know if I have time to wait. Sorry? Still, we don't like to wait 12 minutes for the for the video to buffer. Anyhow, the point here was that, oh, there it goes. Yeah. So anyhow, the point here was that when you add gravity, then you get the prograde to retrograde ratio, which makes sense because without gravity, there is no reason why a clump would orbit in any other way, right? I mean, in one way or the other, there is no preference there. These clumps are in equilibrium between gravity and the centrifugal force. So yeah, you need gravity to make that happen. What is shown here is the eccentricity of the clumps, and here the angular momentum in Z. So, well, it disappeared, but it was showing that most of them were prograde and a few of them were retrograde, and indeed it ends up with the 80-20 ratio. So this conference called Challenges, right? Challenges in planet formation. So I'd like to talk a little in the time that I have left to talk about the challenges that I think are in the future for streaming instability. One of the main ones would be the resolution, of course. That model that I showed had h equals 0.3, which is completely unrealistic. If you want to go to a more realistic scale height and still having the resolution to resolve the streaming instability, the resolution would have to be much, much higher than that, like 6 times higher in each of the grid points. This goes with, and then the number of particles would actually have to be much higher than that too. It seems high, but it's doable. Something that we could do. However, the highest resolution, even in shearing boxes, right, which can say that it's like 10 to the minus 4 of an AU, the grid element is still 10 to the 4 kilometers, much bigger than a planetesimal, right? So we are still quite far from being able to resolve the scales where where collapse happens. Another challenge I would say is the a factor 2, right? That is very annoying, and it shows here. So this is the a model done with the metallicity of the sun, 0.01. You can keep calculating it, and streaming is not going to happen. This is radius here, and then time. Calculate as much as you want. It's not happening here. You need to increase by about a factor 2 for the clumps to start to form. So Daniel did a very exhaustive exploration of the parameter space here. Found that in this region here there is streaming. This region there is no streaming. Chao-Chin looked again at this and then could push it beyond here, so to lower Stokes number, but you still have about a factor 1.5-ish or so from z 10 to the minus 2 to where you get streaming to happen. And as we heard from Martin, this problem will only get worse as you go to multiple dust species. Another point here to make the problem even worse, Orkan calculated the dispersion relationship of discriminant instability, including diffusion, which is then for large grains that will not matter much, but as you go here into alpha values that are higher, right, you end up seeing that the growth rates become very small, so it takes a long time for the instability to kick in. This is here the time, well, the inverse of the growth time, right? So takes you about 10 million years, and in a disk you just don't have that time. So for chondrules, so tau from 10 to the minus 2 to 10 to the minus 2, which is here, and alpha values from about 10 to the minus 5 and 10 to the minus 3, this region becomes quite difficult to get streaming going. Of course, this is analytical, right? The growth rates only. Would need to model that to understand exactly how that will play out in actual simulations. So I would say that this is another challenge. So this is a diagram of where the instabilities are in disks. We like to call this a butcher diagram, as you can see there. Plotting, showing which part in the disk they are. We don't know how the streaming instability will play out with every single one of these processes. We have calculations of the streaming instability with an MRI, with Rossby wave instability. We don't have yet in this larger region of this the space that is shown here. I don't have time to go through every one of these instabilities in detail, so I'll just skip that. But definitely I'm interested in it, so if you want to know more about it, come ask me. Another challenge is that the scales of streaming instability probably will remain unobservable in the next decade, because we are, here then we would have about 10 to the minus 2 to 10 to the minus 3 AU. The observations are now barely able to probe the region inside at 1 AU-ish of in the disk. So to reach that will still take large advances in the instrumentation. But what can be seen are vortices, right? And I would claim that that vortices and streaming instabilities, they are complementary. We show here a model where in a vortex we are triggering the collapse to planetesimals, And we can see that the way that happens is by triggering streaming instability in the vortices. So maybe that's a way that the process can be seen. So I'll skip this part here and reach my conclusions. So dust to gas ratio, when epsilon is about 0.1 to 1, the pressure bumps will be depressed. There is Rossby wave instability at the dust fronts. Not all planets are dust dense, and streaming instability in 3D is still a challenge. So thank you very much, and I'll take questions now.
Questions? Jake?
Very nice talk. Do you have an explanation for why gravity makes it prograde preference? Maybe you did and I missed it.
Have a hunch. Yeah, still need to analyze that and see if that makes sense. But what I think is happening here is that if you don't have gravity, the clumps are concentrated there just by the drag force, right? I mean, like you are concentrating in there. So there is no preference if the angular momentum will point upwards or downwards. Once you add the gravity, then you have a force that is countering the rotation, right? So you can have equilibrium. In this case, the equilibrium is numerical. So,
but how would it know? Why would there be a preference from prograde versus retrograde?
I mean, my hunch would have been that it should be retrograde because of the equivalent shear. That would have been my guess.
Yeah.
Because I mean, that was going to be my question too.
Right.
yeah, still need to check that.
Other questions? So I know that vortices promote streaming instability. MRI promotes streaming instability. Is Umarhan's result, in some sense, an artifact of using a smooth laminar viscosity instead of a true instability that'll provide clumping?
That's a point, yes. So this is done just adding a diffusion term to the equations of motion, right? But if you have actual turbulence, then you have many scales. Yeah, indeed. I mean, like you would have intermittence, and as we know, that's what the particles like, right? To concentrate. So that could be a way out.
Okay. Let's go ahead and thank Wlad again.